So today, what I wanted to do is look at what f prime tells us about the graph of a function. Okay, and this is the problem I'm using to start off the story here. I'm saying draw a function f of x such that it has these three properties. Okay, and a good way to think about these things is remember what f prime tells us. So f prime of x tells us the slope of the tangent line for any x value. You keep that idea in mind, then the problem is not that bad. Okay, so let's look at this second fact. The reason I'm picking this second fact to start with is that it has one x value, just x equals 3. Whereas like these fact number 1, talk about a whole domain of x's, and fact number 3 it is, has a whole domain of x's also. So fact number 2 tells us that the slope of the tangent line when x equals 3 is 0. Okay. So what does a line with 0 slope look like? Well, it looks horizontal. That's m equals 0. Like the x-axis has a slope of 0. Okay. If we think about some other slopes, just that you should know, a perfect diagonal, for example, has a slope of 1. Perfect diagonal that's negatively associated has a slope of -1. And then, for example, maybe a slope in here might be some fraction, so maybe 1/3 or something like that. And any slope over here would have a slope bigger than 1, maybe 3 or 2. And then similar reasoning gives you that this might be -0.5 and that this might be -2. So it's good to keep this idea of what slopes look like in mind. A vertical line has no slope. Okay. You could also say along a vertical line that f prime of that vertical line all along it does not exist. There is no slope of a tangent line because vertical lines don't have slopes. Okay? All right, so if we keep this sense of slope in mind here, then we can draw something that has this property. So let's do that. Let's go over to x equals 3. And what I know is when x is equal to 3 that this thing has to have a tangent line with a slope of 0. Now, I don't know what y value it's at. The problem doesn't tell us, so we have a lot of freedom here. So maybe I'll go up here. I'll put a point right here. Maybe this is like y equals 5, for example. And I'm going to draw a little horizontal tangent line to indicate that the slope there is equal to 0. What I know is at this instant in time, when x is equal to 3, the graph is acting like a horizontal line. Okay? All right, let's go back and look at the other facts. All right, the fact number 1 is telling us that prior to x equals 3, here's 3 down to -infinity, that the slopes of the tangent lines are always bigger than 0. So that means all your slopes are positive before x equals 3. So what might that look like? Well, have to be some kind of picture that does something like this maybe. Here's one possible answer. Now here's why. Look, think about all these tangent lines. If you draw any of them, all of those tangent lines have a positive slope, right? Maybe you'd guess. You'd say, you know what, I think this slope here is 1. And maybe you think that slope's a little bit steeper, so maybe you think that slope is 2. And this looks a little flatter than 1, so maybe the slope is 0.8. But you certainly couldn't tell me that any of those little red tangent lines had a slope that was equal to a negative number. Okay? So here's another way to think about it. When we see this fact that f prime is greater than 0, this is another way of saying that f of x is increasing. Okay? Meaning that as x goes up, y goes up. So you should think of slope as, if you're unsure why this is true, think about slope for a minute. Generally, slope we always thought of as change in y over change in x. In the case of f prime of x, we usually write it this way. We write dy dx. And the reason we write dy dx, dy means a really small change in y, and dx means a really small change in x. And what we know is if f prime is positive, that means every time dx goes up by a little bit, so if this increases by some small positive amount, then y has to increase by some small positive amount. That's the only way the derivative would stay positive. So you divide them, you got a positive number. So this is a way to figure out that a function is increasing. Let's go back and look at fact number 3 now. Maybe it won't seem so bad. This is telling us that from 3 to infinity, that all our slopes of our tangent lines are negative. So what does that mean? That means that dy dx is equal to some kind of negative number. A negative number, that means when x goes up, y goes down. So what does that look like? Well, maybe the graph does something like this. Okay? And then you'd have these little tangent lines here, and all those tangent lines have slopes that are negative. So this graph meets all the criteria. Yeah, right? It has a positive slope from negative infinity to 3. When we get to 3, for that instant in time, the slope of the tangent line is 0. And then after 3, we can see that all those slopes are negative. So maybe, you notice when I've been talking about this, I've been saying the graph may look like this. So here's why I'm saying that. You do have some liberties in terms of how you draw this. So here's another graph which fits the bill. Okay? So watch what happens. This will do it. Okay? And why does this graph work? Well, at 3, for example, the slope of the tangent line appears to be 0. All of these slopes are equal to something positive. All of these slopes are equal to something negative. Right? So, here I've drawn curves specifically. These things are nice curve functions. This looks like an upside down parabola. This looks like a piece of a cosine curve maybe, right? Now we know it couldn't be a piece of a cosine curve because a cosine curve would eventually bend up again. And that would not satisfy the rule. The rule was that the slope stayed positive from negative infinity all the way to 3. So this graph would not have the option of bending upwards. Maybe it bends down again at some point. Okay? Now, you might try and draw something with lines. I would warn you, you got to be careful. Okay? So here's 3. Let's pretend you drew a nice straight line up to 3. Well, this works because all these slopes are positive. So check. That's true. Maybe you drew another line like this, and all those slopes are negative. So everything's good there. And here's where we get in trouble. Question is, does this slope here equal 0? And the answer is no, it doesn't. All right, so we haven't talked about this yet. But what we say at this point is f prime of 3 does not exist. And the reason why is because the slope on the left is staying at x equals, let's pretend, or say, not x equals, but m equals 1. Let's pretend all these slopes are 1 for the time being. And what you'll notice is, no matter what you do, no matter how close you get to this point up here, these slopes all stay at 1. And then if you go just on the other side of 3, let's pretend all these slopes are negative 1 for now. All these slopes stay at negative 1 no matter what you do. So when you get to x equals 3, you've got to be a little bit confused because at x equals 3, what's the slope? Is it 1? Is it negative 1? Right? And so what we generally say is at points, at corners, that slopes don't exist. Let's go back to the other graph for a minute. In the case over here, what you'll notice is these slopes, for example, maybe that slope is equal to 1. This slope, maybe that's like 0.9. This slope is definitely flatter. This might be like 0.5. And then a slope in here looks like it's maybe 0.2. So what's different in this problem is as we get close to 3 from the right, so I'll write that this way, as x goes to 3 from the left, we can say that the slope is getting closer and closer to 0. Okay? And then if you use the same reasoning on the other side, let's pretend we ask about, hey, what happens if we go to 3 from the right? Well, that slope might be negative 1, but this slope might be only negative 0.3. And the slope right here might be m equals negative 0.1. Well, we can say the same thing. As x approaches 3 from the right, the slope is getting close to 0. So in this case, we don't have that problem where we have different slopes on the left and right. The slopes are both coming into 0. Whereas this problem, this stubborn absolute value function, no matter what you do, no matter how close you get on the left side of 3 or the right side of 3, no matter how close you get, the two slopes never get close to 0. They stay at 1 and -1 respectively, and that's why we say the slope at 3 does not exist. Let's try another one. So let's see if we can draw a function that does the following. F prime of x is equal to 0 at x equals 2 and 5, and f prime of x is greater than 0 on the interval -∞ to 2. F prime of x is going to be less than 0 on the interval from 2 to 5, and then f prime of x is going to be greater than 0 again on the interval from 5 to 10. Let's have a little fun here. Let's pretend that f prime of x stays at 1 on the interval 5 to infinity. So can you draw a graph that meets these conditions? Small error here. Sorry, that should say 10 to infinity. So we don't have that then we don't have overlap. So let's give this a whirl. All right, so we know that the slope's equal to 0 at 2 and 5. Now, that gives you some options. Here's 2, here's 5. So maybe you decided, hey, I'm going to make the y value at 2 up here and the y value at 5 down here. So these blue lines, these blue tangent lines represent a possible combination. You might have decided to draw them both at the same y value. Or maybe you made the y value at 2 lower than the y value at 5. What you're going to discover, though, is that only one of those combinations will work with the other facts. So sometimes you have to think about the other facts first before you can really decide where you're going to put these y values. So let's see what happens. We'll just check this off for now, this first one. This is saying that from -∞ to 2, the slopes are all positive. So that means that the original function, f of x, had to be increasing. Okay? This is telling me that between 2 and 5, the slopes are negative. So it means f of x is decreasing. And it turns out this is the important fact. If we star next to this, this fact is going to help us decide what our y values should be like at 2 and 5. And I say be like, I mean compared to one another. So let me show you. So let's think about this. Let's look at the blue ones for a minute. In that case, the graph might have to do something like this. It would have to come down like that. Right? So the blue graph would satisfy that starred condition because the slope was negative in between. The function was decreasing. The red one wouldn't do it. The red one would have to have positive slopes, so that's no good. And the green one would have to have a slope of 0, and that's no good. So the red and green can't work, only the blue can work. Okay? So I'm going to get rid of those, I'm going to get rid of these, and that's what our graph has to look like in between. From the second fact, we knew that the slope was positive before 2, so the graph had to come up something like this and level off. And then after 5, the slope had to be positive up until about 10 on the x-axis, at which point the graph after that always had a slope of 1. So what that means is it can't be curved anymore, has to be a straight line with a slope of 1. So this is a possible graph. So if you had tried to draw a function that did this yourself, there's no guarantee that the graph in front of you looks like this, right? And the reason being is you were never given a y value to start with. So the way I've drawn this graph, it looks like I made f of 2 equal to some kind of positive number. It's equal to whatever I think that y value is. Maybe I think that y value is 4. Okay? But clearly, if I took this whole graph and I shifted it down, so let's say I did this, like that. Well, that dot's in the wrong spot. Hold on a second. This would come down like this, maybe. And then this would come up to about 10, and then it would have a slope of 1 afterwards. This red graph here satisfies all the same conditions with respect to slope, except it has different y values. So now we shouldn't be surprised by this, because if you look at this this set of conditions, they only tell us about the slope of the curve. They don't say what the y values are, which means that this set of conditions basically describes a whole family of parallel functions. So maybe someone decided to draw a graph that looked like this, right? And then a slope of 1 afterwards. All three of these graphs meet the conditions. All three of them are parallel, okay? Usually the way to get around that is sometimes in this list of conditions, they'll say something like this: f of 2 is less than 0. So if they'd given us a fact like that, for example, then of the graphs I drew, the only graph that satisfies it is the green one. F of 2 is less than 0 because f of 2 means the y value when x is 2. And that's only happening on the green graph. The y value on the red graph when x is 2 is something positive. And the same thing with the blue graph. So here's one more fun problem to consider. And it brings up some things we did in the past, right? This is new. It's what we just discussed today in this lesson. But this is an old idea. Can we draw a graph that satisfies that limit, right? And this one here is just telling us a y value. Shouldn't be surprised by that at all. And then this one is just like what we learned about today. So let's give this a shot. So this first fact is simply telling us that f of x is increasing on this interval. And then let's take this factor with it. This is saying by the time we get close to 7 on the left side, y should end up at infinity. Okay? So let's, and we better be careful again. This is telling me that when f is equal to 0, when x is equal to 0, y is equal to 3, or negative 3. Here's what our graph's got to do. It's got to start at negative 3, or 0, negative 3 on the y-axis. And by the time it gets to 7, it's got to increase up infinitely. So the first three facts are now taken care of. It's done. That's all you had to do. Okay? Actually, not quite. I should be careful. Well, no, it's actually all done. I was worried that this was a two-sided limit, but it's not. It only tells what happens on the left side of 7. So I don't have to worry about the right side of 7. This is telling me that f of x is decreasing on the interval negative infinity to 0, so the graph has to come down and do something like this. Okay? So this is a possibility. You do have some options here. They never told us, for example, what f prime of 0 was. Right? So the way I've drawn it here, I seem to be implying that f prime of 0 is equal to 0. There's some kind of horizontal tangent line there. But since they didn't state anything about this, if you wanted to, you could have drawn a graph that did this. It could have come in as a straight line and then gone up like that. So in that case, if you're looking at the red graph, then f prime of 0 did not exist because you've got a sharp corner. Whereas on the green graph, f prime of 0 looked like it was 0. So you'd have options like that if they don't tell you. Also, anything beyond 7, you could do whatever you want. So maybe I'll make the graph do something like that because there was no conditions for what happens beyond 7.